Hello everyone. In this video, we are going to derive an expression for the overall thermal resistance with heat transfer across materials in both series and a parallel. We're going to go ahead and start by doing this in a series. So I have over here the same system that we've been working with, where we have coffee in a glass cup in an insulator exposed to air. So one important thing to remember is the relationship with heat and resistance. So we have our Q, our heat, which is equal to our change of temperature over our respective resistance. So what does this look like in math form? Well, if we go through step by step, we're actually curious about all of the heat transfers in the system. So we're going to do Q equals, we'll start with the coffee to glass over here. We're going to go ahead. Heat transfer is moving along this way. So we're going to start off with a change of temperature, which is T1 minus T2. And if you remember, the resistance that we have is an expression that we've already solved for before. It is, if you think about it, think of what resistance is. The resistance in this case is the absorption of energy throughout our system. So this is the convection of the heat that we are considering for our resistance because coffee is a liquid and it goes by the rules of convection. So that's what we're going to use for our resistance. Now, obviously these Q's are going to equal each other because remember for heat, whatever goes out is going to equal what came in because the rules of thermodynamics would break otherwise. So let's go ahead. We're going to do the same thing for the glass here. We have T2 minus T3. And this is the length over the thermal conductivity times the area. And this is the thermal conductivity of glass. I actually forgot to add this is H of coffee. Now this is equal to the expression for the insulator, which is T3 minus T4, which again, we're dealing with convection over here. This is K of 1. This is the insulator. All right, and now we are concerned with the air, which is T4 minus T5 over 1 over A, and this is for air. I actually forgot, this actually should be better visualized because we have our T4 that's in this sort of boundary layer, and we have T5, which is the actual temperature outside of the system. So just to kind of visualize that for us. So this is actually going to be T5 is the temperature of the air, T4 is the boundary in between. So that is how we solve for that. Now what we're going to do is we're going to say, okay, in a series, if we think about resistivity for voltage, when we have a bunch of resistors together, all we do is we add the total of resistances to each other. It looks something like change of voltage equals our total I. So we're going to do kind of the same thing here. We're going to go ahead and lay out all of the terms with heat, the resistivity, and the change of temperature, and we're going to add them together so that we can have this kind of total expression for heat in this case. So we're going to say, let's see here. And for this, I'm just going to refer to this as the R of coffee. This is the resistance of glass. This is the resistance of the insulator. And this is the resistance of air. And now what we're going to say is we have Q times the resistance of coffee equals T1 minus T2. We're going to do R of glass equals T2 minus T3. Move down here, we have Q times the resistance of the insulator, which equals T3 minus T4, sorry, T4. And then we have the resistance of the air, which is equal to T4 minus T5. So let's go ahead and begin to add these, and we'll see something that's interesting. When we add either side, we have Q as a common term over here. So we're going to have Q multiplied by, and these are all the resistances combined, plus R of the insulator, plus the resistance of air. So we have that on one side. What we also have is on the other side, if we add T1 minus T2 to T2 minus T3, if you look, T2 actually cancels out, T3 cancels out, and T4 cancels out. So all that we're left with is T1 minus T5. So if we want to simplify this, we can say T of the total resistance equals T1 minus T5. And that is how we can derive an expression for the overall thermal resistance, which for a problem like this is going to be the much simpler method rather than trying to individually solve for all of the heat transfers between each and every individual phase. So that is how we do it for a series. So how do we do it for a parallel? I'm going to go ahead and shrink this guy down. Put you over there. Okay, so let's do the same thing with a parallel. Parallel. There we go. So for this, we're going to imagine a new system. We're going to have a temperature 2. Now here's the difference. We have some sort of material. Let's say like this is something like glass, right? Now, beside it, parallel to it is going to be something like wood. And we have a temperature 1. I don't know why I made this temperature 1, temperature 2. I'm going to make this temperature 1, temperature 2. So if you look, this is quite a bit different than our problem here, where we had like coffee as our heat source over here, and it was traveling its heat to the left, and it was being met by a series of resistance. Over here, this is parallel resistance. These two are side by side. So you have to wonder, what does the math expression look like? Well, what did we do for the series? We looked at how voltage works and subbed in the logic from using voltage to figure out our Q for our heat transfer. So we're going to do kind of the same thing again, but now assuming parallel resistors. So let's go ahead and make a very simple parallel diagram for voltage. So I have resistor 1 and resistor 2 in parallel. We have voltage here, a voltage there, and we have our currents 1 and currents 2. Because remember, if you have something in parallel, you're going to have two different currents feeding back in. So how would we solve for this? Well, we know our change of voltage equals our total resistance multiplied by our current. So in this case, what is current? Current equals the sum of current 1 plus current 2. Actually, I put these in the wrong location. More accurate location would be I1, I2. So we can say that current equals the current going into resistor 1 and the current of resistor 2. So knowing that, we can now kind of reverse this equation back and say, okay, well, this current actually equals change of current over the resistance 1 plus change of voltage over resistance 2. And we can say that this is equal to change of voltage over the total resistance. And now if you've noticed, we actually have like terms over here. So now what we're going to say is, okay, to get our total resistance, we can express this as 1 over resistance total equals 1 over resistance 1 plus 1 over resistance 2. Okay, well, that looks pretty simple. That looks like, what is it? This looks like we could actually relate something from our thermal system from the voltage equation that we've just made to figure out how to solve for the total resistance of a system. So let's go ahead and set up an equation that looks like this. So remember, for what is it? For resistance, we say for something like glass, this is going to be involving the thermal conductivity and the area. So we have something that looks like I'm just making sure I got you. Yeah, yeah, okay. Just make sure I put a length there. So let's say we have glass, and we want to find the resistance of glass. Well, the resistance of glass is going to be the negative thermal conductivity of the area under the length of the system. We found this expression when we were deriving a what is it? When we were deriving an expression for thermal resistance. So we know that the resistance for the glass is going to look something like this, and this is going to be the thermal conductivity for glass. And then here we have the resistance of wood, which is the length over the negative thermal conductivity of wood times the area. So these are our resistances. So we look at the resistance that we've just acquired, we have to consider the rules of current. We said that for a parallel series, if we have two separate resistors, that we have two separate currents, and that those currents add up to each other to give us our total current. And now, much in the same way, we have Q, which is our heat transfer, and that becomes an additive property where we can say Q equals Q glass plus Q wood. Now, what can we use with this? Well, we know that Q equals change of temperature over resistance. So we can say we have the change of temperature over the resistance of glass plus the change of temperature over the resistance of wood equals the change of temperature over our total. And now we can express this and finally get our expression 1 over our total equals 1 over our glass plus 1 over our wood. So now we have both expressions of overall thermal resistance for both a parallel and a series. Hello everyone. In this video, we're going to explain the total resistance of a typical home wall with brick insulation studs and a double pane window glass. So I've already made a sketch of what our system looks like, and immediately what's obvious is that we have two series in parallel. So we have our series with the double pane glass, glass one, glass two, in the air, And we have our right side, which is the stud, the insulation, and the brick. So let's think back to how we can find the total resistance of a system. If we know that a system is in series, we know that the heat transfer of the system will be the same going in and out. So the heat transfer from glass one over here will equal glass two, meaning that we can relate them to each other and actually add the resistances to each other to find the total resistance of the sequential series. And once we do that for both sides, if we have two known resistances in parallel with each other, we can then add those two resistances to each other to then know the total resistance of our system. So, what is this heat transfer going to look like if we have uh, this typical home structure with the inside temperature over here and the outside temperature over here? Well, let's go ahead and solve for the series first and find what its resistance is. So, if we imagine the inside as inside air, and we imagine the outside as also just outside air, uh, becomes pretty obvious that this is going to be a lot of convection on this side. So let's go ahead and start by looking at the air going into the glass. Let's go ahead and put this for double double pane glass. We have our double pane glass over here. To get the total resistance, we're going to start from the very beginning. We're going to look at the air inside going into the glass. This is going to be convection. So we're going to have, let's see here, let's see here. We have R convection, so the resistance due to convection from the inside into the glass one that we see over here. So that's our first resistance. Our second resistance is the thermal conductivity of the glass itself. So we can just put that to glass one. And we're going to continue to add these as we go along. So we have glass going into air two. So this is convection. We have convection of air from glass one being added. And then we actually have second convection in this step because we also have the air from glass one, the heat transfer from glass one going into air, and then the heat transfer of the air going into glass two. We're going to add that, and now we have the thermal conductivity of glass again. And then we add that to the outside convection. I don't know why that did that. Outside convection of outside air by the glass. And so if we add all of these, that would give us a realistic uh, total resistance on the double pane glass side. That would give us a system. It's just a summation of all resistances. Now let's go ahead and go to the right side. We're going to just call this the wall. So the wall is probably going to be a little bit more simple because it's a lot more conduction on this side. We have convection coming in from the inside, which then meets the brick. Now we have the conduction of the brick. We have the conduction from the insulation. And then we have the conduction of the stud. And we have the conduction or convection from the stud going into the outside air. Why is this happening? What are we again? Outside. I don't know why. I forgot. Outside, from the stud. That's right. All right. So, uh, now that we have both of these resistances, if we remember from what we said, if we have two resistance in parallel, to find the total accumulative resistance, we can just simply add the two. And so I'm just going to make one giant note here. Our resistance total equals the, let's see, the resistance due to the double pane glass plus the resistance due from the wall. And that is how we could find the accumulative resistance for this system.